the gradient is something we're going to use today, and this was introduced over the videos. A lot of us have heard the word gradient, but we don't exactly know what it means. The gradient is how I turn a function literally into a vector. It's kind of a crazy thing. The gradient turns a function into a vector, so you take the gradient of a function, it produces a vector. You don't take a gradient of a vector. So the symbol, it's called the del operator. Okay, if you watch the video, you understand that. So if I do this on f of xy, or let's say g of x, y, z, you're only going to do gradients of functions of 2 variables or functions of 3. There's really no use for higher levels. Not that you can't do it, but there would be no physical application for a gradient of a 4-dimensional, 4-variable function. Okay, so what is this? It's the vector of partial derivatives. Okay, my original function is not a vector. The gradient turns it into a vector. Okay, and then we use this to answer a lot of questions. We're going to use this today. So one of the things that I proved in one of the videos, I proved that the gradient vector is in what direction? Let's see if anybody watched. Anybody know? Oh, this is important. Yeah, this is one of the more important geometric proofs that we do in Calc 3. The gradient vector points in the same direction as the outward normal. That's astronomically important. Yeah, that's on the. Actually, I don't. That would be the chain rule directional derivative gradient from Saturday. So you want to make sure you look at that one. The proof is actually not very complicated, but it's a huge result, and we're going to use that today. Now, in and of itself, it doesn't mean anything to us yet. We're going to create this, and then we're going to use this. Okay, so again, I have a function. So one of the things that I showed you when we had the directional derivative. Okay, let's go back to Cowles Mountain now. I'm climbing up Cowles Mountain, and so while I'm climbing up Cowles Mountain, right? I said, "Oh, Summer, I'm going to climb Cowles Mountain." She goes, "Oh, how steep was it?" That's a trick question, isn't it? Well, I'm standing here. I'm in the middle of Cowles Mountain. I'm standing here, and you say, "How steep is it?" Well, it depends. Depends on what? By the way, this is going downhill now, isn't it? When you say how steep is it, if as I turn 360 degrees, aren't there an infinite number of possible answers to that question? Oh, so it's not how steep is it. How steep is it in what?
That direction.
In that direction, whatever direction. I have to have a direction. So when you're standing on Cowles Mountain, and anybody who's ever climbed it, you know, you say, I want to make it hard on myself today, so I'm always going to pick the steepest, most difficult climb, or you're going to pick the easiest. Maybe you're going to do a lot of zigzagging, right? Do you all agree with that? So I'm climbing, the direction that I choose completely determines how steep it is. And the way I said last week is, I'm going to take a slice. I have a big saw, and I'm going to slice Cowles Mountain. And now what I see is the rim. I see a 2-dimensional curve. That's very critical. I see a 2-dimensional curve. So the tangent line where I'm standing, the slope of that tangent line would tell me how steep it is. But if I slice in a different direction, I get a different 2-dimensional curve. That's why this is called a directional derivative. Because when you ask for slope, slope is 2-dimensional, period. But we live in a 3D world. So it's always the slope in what direction. And the moment you pick a direction, now you have a 2-dimensional slice. Okay? But when we did partial derivatives, we said, well, let's pick a y value and slice it. And then when we look at the xz plane, we can talk about partial derivatives. Or I took an x value, I sliced it. Now I'm looking at the yz plane, and now I could take partial derivatives. That made it easy. But what if my slice is this way? Then what I do is I take a linear combination of those two. Oh, that's why we started with only the slice in the x direction or only the slice in the y direction. The directional derivative is a slice in any direction. That's why we need the unit vector in the direction we're going. You see, going back to the partial derivative, if I said I'm only looking at the xz plane, then technically we're taking the unit vector in that direction. We're taking the unit vector in this direction. So what if I want to slice it, 45 degrees? I need the vector in this direction that's still a unit vector. So it's going to be a sum of this, sum of this. That's why you always took your direction and made it a unit vector. So again, Liam, I need you to go that way. How far is that way? Forever. Oh, I need you to go that way 100 feet. Okay, so what do? Make that way 1 foot long, and now multiply that by 100. Okay, we've been doing that since day one. That's the idea. If I make my direction a unit vector, then it does not contribute to the answer in terms of magnitude, only the direction. So on the directional derivatives, we make our direction a unit vector. Now we complete the problem. So that's, hopefully you guys get that from the videos and so on. So today what I want to do is actually come up with how do we make a tangent plane. So I want you to think of a surface, any surface. I'm fluffing the sheets as I'm making my bed, and I do a freeze frame, and I see hills and valleys. Pick any point on the surface, and clearly there's a tangent plane. I could take a basketball. At every point on the basketball, I can think of a tangent plane. You don't talk about tangent planes to flat things. That'd be boring, wouldn't it? If I said, what's the tangent plane to this wall? Well, it would be this wall. And that's not interesting. Do you agree? But if I said, let's take something curvy, like your little pouch there. If you hold up your pouch for a second, that's not flat. So if we said pick any point on that pouch, we could talk about the tangent plane at that point. Now, how do I describe a plane? Always with the normal vector. So then I remind you, we did this where I gave you 3 points on a surface. You created 2 vectors, you took their cross product, you came up with this vector. You came up with the normal vector. But how many planes use that normal vector? Exactly how many planes use that normal vector? Infinitely many, and they're all parallel to this one. So once I have the direction, what else do I need? I need a point. Hey, in the xy plane, once I give you a slope, don't you need a point before you can tell me the line? Otherwise, all your lines are parallel. Okay, so it's the same idea. If I give you a point and I give you a normal vector, you can easily describe the equation of the plane. Okay? That's easy, but that's because I started with 3 points on a plane and I asked you to produce that plane. That was easy. That didn't require any calculus. That's what we did, I think, on our 3rd lecture of the semester. Now I'm doing something completely different. Now what I'm going to do is say, I'm going to give you a surface. Okay, that kind of represents a 3-dimensional surface. You can all see that. I want the tangent plane, let's say, at that point. So there's a plane. I have a surface. At that point, there is exactly one tangent plane. But how am I going to determine the plane? It's based on the normal direction. So let's say that's the normal direction. So I'm fluffing my sheet. I got a little hill here, and I'm picking that point there. So maybe my tangent plane is right here. How do I know? Because the outward pointing normal would be in that direction. Okay? So all I need is the normal vector. And let's, for lack of a better name, let's say it's ABC. Let's say we know that normal vector. This is z equals f of x comma y. That's my surface. Let's call this point right here x naught, y naught, f of x naught, y naught. Technically, you could say x naught, y naught, z naught, where z naught is f of x naught, y naught. That's also a typical way of saying it. Okay? And if you want, I can say call that one z naught. Okay. So if I said, what is the equation of the plane? We've done this before. You would say it's n dotted with x minus x naught, y minus y naught, z minus z naught. Do you all agree with that? I mean, that's what we did. Oh, that's right, because the normal vector is orthogonal to every vector on the plane, and all I got to do is set this equal to 0. Then every point on the plane, remember, if I pick another point on the plane, then the vector I create is always orthogonal to the normal vector. Ah, that's a piece of cake. I give you a function, I give you an x naught, y naught, z naught, and all I got to do is do this dot product. Just one teeny little detail that all I got to do is I gave you that and you calculated that, and I just got to dot it with the normal vector to the surface. That's all I have to do. Does anybody see a potential problem here? How do I find the normal vector to the surface? Oh, yeah. Oh, somebody will just give it to me. So when I'm fluffing my sheet, I'll quickly go to Google, what is the normal vector to the fluffed sheet? Don't think that exists anymore. We got to figure out the n ourselves. But what did I just say a little bit ago about the gradient vector?
Always points the same direction as.
It's always the same direction as the normal, always. Now, I drew what's called an outwards pointing normal. Could the normal point in the opposite direction? Yeah, this isn't a closed shape. If I had a sphere, you don't really think of normals pointing to the center of the sphere. You usually think of them pointing outwards. But if I just gave you a random curve throughout the room, who says which direction it points? And the reason that's not important is because opposite direction just means you're multiplying it by -1. Will that have any effect on this equation? No. Because of the 0, it doesn't matter what direction it points in all actuality. But I need the gradient vector. Okay, so let's just take the gradient. So if I take the gradient of z, which is the gradient of f of x, or f of xy, excuse me, that's easy. Except for, again, one small little detail. Tell me about the gradient of f. Do you agree that that's the gradient of f? Do I have a problem? Yeah, why? There's a problem still. You should all recognize it.
Where is z?
Can't quite do that. Why?
There isn't a z.
I have a 2-dimensional vector and I want you to dot it with a 3-dimensional vector. That operation does not exist. Ugh. So that can't be the right thing to do yet. I need a 3-dimensional vector. Okay, let's make one. Or I should say a 3-dimensional. Yeah, I need a 3-dimensional vector, so I need to create something that I can take the gradient of. So we're going to create a new function. We'll call it, how about g of x, y, z? And you know what it's going to be?
Z minus
F of xy minus z, or z minus f of xy. Thereby making my surface, my specific surface, a level surface of this. Remember, everything in 2 dimensions is a level curve of something in 3. Now I'm giving you a 3-dimensional surface. Is there anything wrong with that being a level surface of something in 4? Nope. But that's how I'm making my 3-dimensional gradient. I'm going to take the gradient of this. Can I always do this? Yes. Now, it does not matter which order you subtract in, for the simple reason that you're setting your dot product equal to 0. It does not matter what order. But a simple rule of thumb that most people follow, because it will matter later. How do I know which one of these to choose? If I know what the surface looks like, then it makes it easy. Is my normal vector pointing above the xy plane, or is it pointing below the xy plane? In general, what do you think in this case? Is it pointing upwards or downwards? It's pointing upwards, which means when I take, I'm going to show you. When I take the gradient of g, what am I going to get? fx, fy, what's the derivative there? -1. Remember, I'm taking the derivative of this quantity with respect to x, then I'm doing it with respect to y, then I'm doing it with respect to z, or my gradient is -fx, -fy, +1. It's one of these two. It actually doesn't matter in the case where I'm finding the tangent plane. It does not matter. Later on, though, when we're doing certain calculations, and we're going to actually be doing dot products and things, and not getting 0, it will matter because I may be calculating work, and I could get a negative answer rather than a positive answer if I choose the wrong one. So it's a good rule of thumb to say, you know what, I'm going to choose the one where it's pointing in the right direction. But for this, it actually does not matter. So most people just go ahead and use this one. Again, but later on, it may matter, because I may be calculating something with units, and my answer is not going to be 0, and positive versus negative can matter, okay? Does everybody understand? That's it. I just had to make it graded. So, I'm going to change this now to fx, y, -1 dotted with this. And when I do that, I'm going to get what? This, by the way, these are evaluated, just so you know, these are evaluated at x naught, y naught, z naught. So I'm going to get, I'll write it out. I'm going to get this evaluated times x minus x naught plus fy evaluated at x naught, y naught, z naught times y minus y naught. And then the last one is plus -1 times z minus z naught. This is the place where people usually make mistakes. They forget the -1 because they didn't have to do a partial derivative to get there. So we're going to do an example, a simple example. Okay. We'll do it over here. Let's consider something as simple as a circular parabola, okay? One of my personal favorites. All right? And let's pick a point on there. And let's say the point is, how about, so I'm down on the XY plane, you know, and I'm going to shoot up. On the XY plane, let's take the point and say 4, 3. Okay, that's a terrible picture. Okay, so on the XY plane, my input is going to be the point 4, 3. So what is this point? It's 4, 3, f of 4, 3. What is f of 4, 3, by the way?
25.
25? So it'll probably be easier to just say 4, 3, 25. There's a point right here. 4, 3, 25 on the outside of my surface. So there's the origin. It looks like this. Right? It's my paraboloid, my bullet shape. I like to think of my bloomin' onion. Right? It's going out here. Now, I went out 4 units, 3 units, and then way up to 25 units. Now, tell me about the tangent plane. Tangent plane is going to kind of look like this, isn't it? Because it's going this way. The tangent plane is not going to be tilted this way. It's going to be, because this thing is growing, it's going to be tilted this way. So tell me about my normal vector. Is my normal vector pointing upwards or downwards?
Down.
Does everyone see that the normal vector in this case clearly is going to be pointing downwards? Okay. The normal vector at the origin is going to point which way? At the origin, which way is the normal vector going to point, you think?
All.
Straight down the z-axis. Because what's the tangent plane going to look like at the origin? Won't it be the xy plane? Does that make sense? Think of a parabola in 2 dimensions. Your x-axis would be the tangent line. Okay, so my 3-dimensional paraboloid, the xy plane clearly would be the tangent plane, and the outward pointing normal would go straight down the z-axis. So it makes sense that my normal vectors are pointed somewhat downwards. Does it matter? No, but it makes it really obvious that this is the one I want to use then.
What if you have a surface that's like folded in on itself, so there's a, like, you're trying to take the normal at a point where it cinches down to just...
Well, it might not be a function though, what you're describing. So then we have to, I'll show you what we do next. There's a more complicated version. Zachary's question was, what if I have complications? Let's leave it at that. And we'll address that one too. Okay? So I want this, so what I need to do is first of all create a new function. Okay? So how about I say, let g of x comma y comma z equal what? If it helps you, remember this is z equals. Let g of x, y, z equal what? X squared plus y squared minus z. Exactly. That's the best choice I could make. I could subtract in the opposite order, and there would be nothing wrong with that in general, but it does have my normal pointing in the opposite direction, and down the road when we do certain types of calculations, and those are the last third of the class. The last third of the class, this is a common procedure that we're doing where we're making a new function and all that, and you have to decide, and then it's simply looking at the shape. I'll give you an example. We're working with a sphere. A sphere is not a function, but if I take the top half or the bottom half of the sphere, those are functions. Kind of like semicircles in the xy plane. So if I take the top half of the sphere, don't you agree that the normals are all pointing upwards? But if I took the bottom half, all my normals are pointing downwards. So I would actually change the order of subtraction, and that actually will make a difference in calculations. I'm not talking about a tangent plane at this point. I'm actually talking about using these calculations for bigger things. Okay? So we've got this. Now I just need the gradient. So what's the gradient of g? You're doing this right here. So what is it?
2x, 2y, negative 1.
2x, 2y, negative 1. So now technically, what is the gradient evaluated at 4, 3, 25? I don't want the gradient vector as a function. I want the gradient vector of scalars because that's what I'm going to do. This is true. This is true, but this doesn't help me find a specific tangent plane. I want to find that tangent plane, so I actually need to evaluate this. I'm done taking derivatives. That's why it's okay to evaluate now. So what would we get?
8, 6, negative 1.
8, 6, negative 1. And I'm going to choose this as my normal vector. Okay? You just basically stuck those numbers in here. So what do I do with the 25? Well, that's a constant. It's a negative 1. Well, where will the 25 show up in my answer? It's got to show up somewhere. It will. It'll show up right there. Now, it's not arbitrary. So let me kill this spot over here. All right, so the equation of this particular tangent plane will now be, is it 4, 3, 25? So technically, it's going to be 8, 6, negative 1, dotted with x minus 4, y minus 3, z minus 25, and I'm setting that to 0. And most of us know we could have really just jumped to the next step, which is 8 times x minus 4, plus 6 times y minus 3, minus 1 times z minus 25. Again, most errors are made right here. I've seen this for a million years. People forget the negative 1, and so they have an equation of a tangent plane that's missing the z. Probably not good. So what do we get? We got 8x minus 32 plus 6y minus 18 minus z plus 25. So when all is said and done, I'll put it up here. I've got 8x plus 6y minus z, negative 32, negative 18 plus 25, so minus 25 equals 0. This is the tangent plane on the surface at this point. If you had done your subtraction in reverse order, what would be different about your final answer? Negative, negative, positive, positive still equals 0. It'd be the same as if I multiplied by negative 1. So that's why I know it's still going to work. Can I tweak that if I want? If it made it easier on me to manipulate it? Sure. I don't really think there's going to be a reason to do that in general. Okay, questions so far? So I give you a surface. Finding the equation of the tangent plane is nothing more than create a create a four-dimensional function where your surface is a level surface of that. Take the gradient of that guy, so now you have enough variables, and then do this. The process is actually very, very simple. All right, there's just nothing complicated. Well, what if this is really complicated? But you're taking partial derivatives, which hopefully now you've done a few partials to notice that partial derivatives just aren't very complicated in general. They're not difficult to do, okay, which is nice. So, next thing, what if? I now have a function of 3 variables, which technically means I'm now 4-dimensional. I'm going to give you a very specific input, an x, a y, and a z. When I do that, I will have a value, but I'll also have a point in 3 space. I want the tangent plane of this level surface in 3 dimensions. It sounds very complicated. Actually, it's exactly what we just did. But there's a big difference. I don't have to create a new function. Okay? Now x, y, and z are independent variables, so I don't actually have to calculate them. I'm given them. Okay, you would have to be given these. You don't have to worry about that part. Over there, I was given the input, and you had to calculate the 25 because I needed a third number. So how do I do this? Well, it's actually the same thing. I'm going to take the gradient of f evaluated at x naught, y naught. Sorry. The gradient of f evaluated at x naught, y naught, z naught. That's a vector in 3D, and I'm going to dot it with x minus x naught, y minus y naught, z minus z naught. Well, this looks kind of the same as what we just did. It's almost the same as what we just did. The difference is I already have a function of 3 variables. I don't need to create one. So you could argue this problem might actually be easier than the previous problem. Interesting. All right, let's do one. I want to choose something where my level surface is a sphere, because that's interesting. So let's consider f of x, y, z is x squared plus y squared plus z squared. This is a 4-dimensional function. But for every conceivable input, every ordered triple you give me, think constants. You give me an x, a y, and z, they're constants. And I plug them in there, I'm going to get x squared plus y squared plus z squared equals some constant. I'm going to get a specific sphere, aren't I? So every level surface is a sphere, and every one of those spheres will have a tangent plane at the x, y, z in question. It's just this one is easier to work with than the one that's already in 3D. I'm going to show you. The one where I give you, let's say, half a sphere or something, or I ask you to find it, this one's nicer, and I'll show you why. So let's find the tangent plane, let's say at -2, 3, -1. Let's keep it simple. I want to find that particular tangent plane. Okay? The nice thing is, I'm not going to get anything weird. I'm not going to get imaginary numbers. I can't get something impossible because I'm squaring the x, the y, and the z, adding them together. So the quantity here can never be negative. Can it be 0? How?
Or wait. All 3.
Yeah, if all 3, if I input the origin, I'm going to get that. Okay, that's what's actually called a degenerate sphere. It's just one point. Okay, that's a whole whole branch of physics and theory. It's very, very cool, but we're not going to go there. All right, no input, no real input I give you could possibly produce negatives here. So that's a good thing. So I'm not going to get anything weird, no imaginary numbers, nothing like that. So I've got this. Let's start by just calculating that. What is f of -2, 3, -1? Let's start with that. So I'm going to get 4 plus 9 plus 1, or 14. Okay. So I'm actually asking you to find the equation of the tangent plane to the sphere x squared plus y squared plus z squared equals 14 at the point -2, 3, -1. Okay? Is everybody okay with that? So let's find the gradient. Well, that's nice. 2x, 2y, 2z. Let's find the gradient evaluated at -2, 3, -1. And I get -4, 6, -2. So now the equation of my tangent plane, I'm going to take this, and I'm going to dot it with x minus the x coordinate, y minus the y coordinate, z minus the z coordinate, and I'm going to set it equal to 0. Okay, this process should feel very familiar about right now. So I get negative 4, x plus 2, plus 6, y minus 3, minus 2, z plus 1, all equal to 0. So negative 4x minus 8, plus 6y minus 18, minus 2z minus 2. And I'll move that over here. So the equation of the tangent plane that I'm interested in is negative 4x plus 6y minus 2z, so minus 8, minus 18, minus 2, so minus 28 equals 0. That's it. Wow, that just wasn't that bad. If I give you a function of 3 variables, it's a 4-dimensional problem. So how do I discuss a tangent plane? It's the tangent plane to a specific level surface that you're asking. Okay, that's why you have to have the input. And then the rest of the problem self-navigates pretty much. This problem here, most people actually find simpler than the 3-dimensional problem. Why? Because I didn't have to do anything. I just took everything as is at face value. The other one I had to create a function, I had to tweak it. But the first one that I did is the more valuable of the two in that we're going to do that one far more often. You're going to have surfaces that are functions of 2 variables far more often than you're going to have functions of 3. So now I want to go backwards, and I want to do another sphere problem. Question?
So the value of z in 3 dimensions is, in the gradient is always going to be 1 or negative 1?
If it's a surface in 3D to start the problem, yes. Because I have to go f of xy minus z or z minus f of xy. That's not the case here, because this was a function of 3 variables. The problem that you're asking about, on my surface, we usually think of z as the dependent variable. It doesn't have to be, it just is easier mentally. Okay? In Calc 1, you generally used y as your dependent variable and x as your independent variable. But was there anything wrong with taking a sideways parabola and asking questions about it? No, you just hated doing that because you had to kind of reorient your thinking. In this class here, the way it's usually going to work is z, we're usually going to choose z as a function of x, y. So when I'm giving you 3-dimensional surfaces, I like to call it floor and ceiling. You know, this is my floor, this is my ceiling. But is there anything wrong with that being my floor and that being my ceiling? Or that being my floor and that being my ceiling? Is there anything wrong with that? No, but I have to kind of tweak how I'm looking at it. And you say, well then, technically, doesn't every conclusion we make literally have 3 versions? Yes. Every formula we come up with from here on out, many calculus books will give you 3 versions of it. And that's very confusing. I laugh at that. You know why? Because when you go out in the real world and I'm saying, here's my physical object, you can orient x, y, and z any way you want. So you will always choose this orientation. Nobody on the right mind would choose this or this. Because you get to choose the orientation of the shape. Does that make sense? You're never given a function and asked to deal with it. No, you're given a situation and you create the function, so you're going to do whatever's easiest. That's why I said when you go outside and I want to know what is the acceleration as a linear combination of the unit normal and the unit tangent, you don't need coordinates. You say, well, my unit tangent is pointing in that direction, my unit normal is pointing in that direction, so I want 10 of these and 20 of these. I don't need coordinates. I need scalar multiples. And by the way, from a visual and a conceptual, that's much easier to deal with. You know, it'd be kind of like saying, Zachary, walk that way 50 feet and then make a hard left 20 feet. Do I need to give you coordinates or write it out as a vector? No, you just do it. It's kind of easy. What we do outside is not the same as what we do in theory on the board. That's why we have to have 2 versions of many things. So I understand theoretically, but then I also have to be able to see it conceptually. In this case here, you have things and you're out in the real world. So you're working with a sphere. You're working with a sphere and you're doing mathematics of a sphere. And your sphere has a particular radius. What your sphere doesn't have is a center. I'm talking about coordinates. Right? So Liam's asked to find the surface area of a sphere or do something where at every point there's a different density and you're finding math. It's complicated stuff. But your sphere, let's say, is, 20 centimeters radius. Okay, great. That is easy. That's not calculus. So now you're going to start doing the math. Oh, shoot. My sphere is over here. Where's the origin? I know where my origin is. Where's your origin, Samuel?
Center of the sphere.
Center of the sphere, yeah, yeah. My entire coordinate system is going to be, now when I carry my sphere over here, my coordinate system followed me. Wherever my sphere is, I'm going to put the center of the sphere at 0, 0, 0, because now the math will be really easy. Can you do that? Yeah, that's how it always works in real life. You choose the coordinate system and where it is. Everybody understands that, because when you go out in the real world, I was checking this morning and I could not find the z-axis anywhere. I think it was hiding behind like the cell phone pole or something. I don't know. I have fun with that because a lot of people keep forgetting that you're learning math that you're only going to apply in the real world. You're not going to apply it pencil and paper in theory. So we have to learn it in theory so we can apply it that way. Now, where's my eraser? Let's do a sphere, not the four-dimensional problem, but an actual sphere. And again, we tend to, I don't want to say water down, I don't want to say dumb down or oversimplify. But when we do the mathematics of these problems, we choose to create it so that our spheres are centered at the origin because it makes the algebra just a lot less taxing. But you say, but don't I have to do something else? Well, again, if you get to choose the orientation, you would have picked the origin anyway. So why don't you practice the math that way? Consider the following sphere, okay? How about at, negative 2, 4. My x and y input will be negative 2, 4. Now there's a problem here. I did not give you a function. So I want to do the top half. Because don't you agree there's two different z values for an input of negative 2, 4? The z would be a plus or minus. Okay, so I have a sphere. I picked a particular point on the xy plane, and it's certainly going to go up to a point on the sphere, but it's also going to go down to a point on the sphere. So there's a point above the xy plane, there's a point below the xy plane. So I have to specify which one I want. That can't be ambiguous. So I said, I want the one on the top. You with me so far? So what that means is, the first thing I have to do is rewrite this as a function. Now, because I said top half, then we want to use the top half of the sphere. If I'd said bottom half, we'd use the bottom half. And we're going to exclude the other guy. So what does z equal then? Now, if I said solve for z without any other instruction, you would write a plus or minus, wouldn't you? That's why you know it's not a function, because of the plus or minus. But because we said top half, let me give you a simple instruction. I want you to get out your graphing calculator and like you to graph a circle, a simple circle. Can you do that? On your graphing calculator, can you graph a circle?
Yeah.
You got to be smarter than the calculator. How do you graph a circle? I agree.
Well, there's a
Yeah.
input.
You graph two graphs. You graph the top half and you graph the bottom half as two graphs, and now you see a circle. Why? Because a circle is not a function. Oh, I need to graph two functions. And we don't have any problem with that, but we realize sometimes I got to do extra. And same thing if I wanted to do a hyperbola or an ellipse. I got to figure out, y equal positive, y equal negative roots. So I want a whole sphere? No, I want the top half, because if I have a whole sphere, I might have a normal pointing up and another normal pointing down, and I don't know which one I'm supposed to use because I'm at two different places. So I'm picking the one on the top half. I could have said bottom half, but now that automatically makes this what I'm looking at. Now that means my gradient vector is going to be way more complicated. Why is it going to be more complicated? Because I got to differentiate that guy. That's why I said you liked the other problem better, because you didn't have to solve for anything. You just took the partials as is, and that problem seemed so much easier, and it was. But this is the more realistic problem.
So right here you solve for the z from the equation of the sphere given, right?
Yes.
So If it was the bottom half, would it?
Then what would we do? You'd put a negative,
Oh, that's not good.
because I need negative z values. Do you all agree that it's z is plus or minus the root? But if I want a function, I have to choose one or the other, so we're going with the top half.
Okay.
That's it. That's not complicated, but what it did, it made it a complicated derivative in a sense. And we are going to work with this shape very often. What is this shape called?
Semicircle?
That's a great question. Little vocab time. Circle, sphere. I want half. I want that half. I want that half. This is one of these things where if you're a mathy person in general, it is always goofy when you get vocab incorrect. Because you're saying something mathy and you get the word wrong. It tends to make you sound like you don't really know what you're talking about. How many have ever had statistics? Okay, one of the most important statisticians, a guy named Thomas Bayes. You ever heard that name before? There's a whole branch of statistics called Bayesian statistics. I mean, people will study that, get their PhDs in it. But there's also something called Bayes' formula and Bayes' theorem that you use in stats. It's kind of cool. It's a really complicated formula, but it's really, really cool. That's his name. So how do I spell Bayes' formula? Well, Bayes' theorem. You put a little apostrophe after the S, because the name ends in an S. I was taking graduate statistics courses at State a few years ago, and they have a really bad habit at that place. The previous instructors don't erase the boards. I never understand this. Has anyone taken classes in the university? It's not unusual that you walk into a class and the boards are filled with writing and the new instructor has to erase it. I followed somebody last semester and I told them on day one, erase the frickin' boards. I'm not going to do that for you. Oh, they don't do it at university. This isn't a university. This is just common courtesy, plus ink dries. So they started erasing the boards. They're filling up the boards and I had to spend 5 minutes erasing the board before I can start. But the previous instructor left all the writing on the board and they were discussing Bayes' theorem. And this is what they had. Bay apostrophe S theorem. And I went, oh my God. I said, you had an idiot teaching the previous class. And people were laughing. I go, no. I guarantee you they probably got the formula wrong. It took 30 seconds for everybody in the room to identify they had the formula completely wrong. They just spent an hour and a half teaching students the wrong formula. And I knew they had the formula wrong because they couldn't even spell the name of the person that it was named after. That's what I mean. When it comes to vocab, we don't want to make vocab mistakes because it makes everything else sound less mathy. But this is a very important vocab word that we should know. This is called a semicircle. And this is called a hemisphere. Okay, what the heck just happened? What does hemi and semi mean? They both mean exactly the same thing. And some of you, I've explained this. Have you heard my explanation? You know this. It is actually Latin. S and H, many words in Latin, it's the same word. And so when I teach remedial algebra, I actually spend time going through all of the Latin prefixes, 1 to 10, and 100, 1,000, a million, and so on. And I do this every semester when I talk remedial algebra. Why? Because you need to know, if I'm talking about, the sum of the angles of a regular octagon, and you don't know what octagon is, it's, seems kind of silly. But now you're in chemistry. Oh, a parabenzoic acid molecule, or, hydrogen monoxide versus hydrogen dioxide versus carbon monoxide and carbon dioxide. Well, one you exhale, one kills you. It's really good to know what those mean because they're all Latin prefixes of numbers. Did you know that? See, there's 2 numbers for 6. What are they? Well, a 6-sided figure is a hexagon. Okay. But somebody in their 60s, it's my favorite words. Somebody in their 60s is a sexagenarian. You're laughing. No, that's actually the word. See, sex and hex mean 6. If you have 6 babies at once, they're not called hextuplets, they're called sextuplets. Sex is 6 in Latin, so is hex. How about 7? A 7-sided figure is called a septagon, but if you run a race in the Olympics, if you do the race, the men have something called a decathlon that is 10 events, the women have something called the heptathlon, which is 7 events, because hept means 7, but so does sept. It's the H and the S. Many words in Latin mean the exact same thing, but it's a context thing. So, do you sound silly if you said, I want you to find the angles of this sexagon? That would sound kind of goofy, wouldn't it? Because we all accept that it's a hexagon. But if we don't know the Latin and when to use it, I might misname things. A hemicircle and a semisphere. Is there any problem, really, if you said that? No, but you'd confuse people because they've never heard that. So what we typically do with hemi and semi, just to make it easier, if it's 2-dimensional, we use semi for half, and if it's 3-dimensional, we use hemi. That's kind of the simple rule of thumb. But it's understanding that the Latin prefixes are all throughout, and I mean from the geometry standpoint. So we're talking shapes, and I said a pentagon. What am I saying? A 5-sided figure. But an octagon would be a 8-sided figure. Is it good to know that kind of stuff in math in general? Sure. How many have had chemistry? How many have had organic chemistry? Most people tell me the hardest part of chemistry, particularly organic, is the nomenclature. Nomenclature is the naming of things. It's vocab. It's not actually chemistry. It's getting the vocab right. Oh, because I can't do stuff if I don't know what the words mean. So in our sense, we use vocabulary all the time, but if we're not absolutely certain what it means, we can get in trouble. So if I say top half, you're saying that the upper hemisphere. And when you're communicating, I just think it's really good to have the right vocab, because otherwise people will say, what is it you're trying to say? What are you saying again? I've never heard that word before. I've never heard of a semisphere, although I don't know why. We don't call it a semisphere, we call it a hemisphere. And I've never heard of a hemicircle, but I don't know why we can't. So I want to do this, which means I need to take partial derivatives of this guy, so I got to go a little bit slower. So this is going to be my f of xy, but now I need to create a 3-dimensional function. Wait a minute, why can't I just use this guy? You can't use this guy because this is not a function in 3 space. So this feels kind of like we're going backwards, but this is how we're going to have to do it. Now, by the way, which way do my normals point on the top half of the sphere? Do they point above the xy plane or below? Above. So which way should I subtract? Function minus z or z minus function?
Function minus z.
You just told me if they're pointing upwards, then I need the partial with respect to z to be the positive one, because the negative one would mean that way. Does that make sense? That's how you make the conclusion. Oh, all my normals are going to point upwards, so therefore, when I create my function of 3 variables, it's actually better form to write it z minus. Now, I'm going to write it this way. It'll make my derivatives a little bit easier to take. Could you do it the other way? Yes, you could go the other way. But we're going to find down the road that could lead to issues, because if I have my normal vector pointing in the wrong direction and we're doing calculations that do not produce a 0, by the way, other than the plane, you're never going to see a 0 again. You're always going to be calculating something. Maybe it's work, maybe it's surface area, maybe it's something else. And I need these to point in the right direction. So I'm just showing you right now, this is how you decided. Well, why is it z minus? Because when I take the partial derivatives, when I have number, and either 1 or -1, oh, +1 in the z means I'm pointing upwards, -1 in the z means I'm pointing downwards, regardless of where I'm pointing in the xy plane. You see, all of my z's right now are positive, regardless of what x's and y's are. Now, if I'm going this way, all my z's are negative. Okay? So, when we do this gradient now, all right, partial with respect to x. Well, here's what I'm going to do. I'm going to do it off to the side. So, I want to do the partial with respect to x, because I'm going to have to do some simplifying. So, what are we going to do? This is going to be 0. Bring down, right? So -1/2, 36 minus x squared minus y squared to the -1/2 times the chain rule factor, which would be Okay, it's thing to the 1/2, so it's 1/2, thing to the negative 1/2 times derivative of thing, which would be negative 2x. Now, oh, that works out very nicely. So how about if I write it like this? Would that work? That would probably be the most useful form. It's not more or less correct than anything else, but it'd probably be the one that's the most useful. So I'm going to put that here. Now, I said laziness is a key virtue of any good math person. Look at the form of my function. I have a negative x squared and a negative y squared. I just took the partial with respect to x, and look what I got. Anybody want to go out on a limb and tell me what the partial with respect to y is without doing any work?
Y over.
Yeah, it's going to be y over, because the form is exactly the same. This is the proper execution of lassitude. And everyone sees that, yes, you know you're going to get that because now you're doing the same thing but with respect to y. So you're going to multiply by negative 2y and so on. Now, what's the partial with respect to z? Positive 1. This is more work than most problems. But we're doing this problem because this type of thing is going to come up fairly often, and I want you to be totally comfortable with this. Not memorizing results, but the process of how to do it. So now I have my gradient, but that gradient is a gradient of functions. I need a gradient of scalars. So at some point, I need to deal with this. So going back to here, what is f of negative 2 comma 4? If I replace x with a 2 and y with a 4, what's going to be the value of the z?
4.
So it's 36 minus 2 squared minus 4 squared square root. That comes out exactly 4. Mr. Brown was very kind to you. No square root there. Is that important? Yeah, that's the z part. So, the equation of my tangent plane, it's going to be, first of all, I need to do this at negative 2 comma 4 comma 4. Okay, I need a gradient vector of scalars, not of functions. So when I replace, tell me what I get. Negative 1/2, 1, 1. Does everybody agree with that? I think that's right. Because when I replace the x and y with negative 2, 4, you already know you're going to get 4, because you just did that a moment ago. So you're going to get negative 2 over 4, 4 over 4, 1. Okay? Not the worst thing ever. So now the equation of my tangent plane, so x minus the x coordinate, y minus the y coordinate, z minus the z coordinate equal to 0. So that's a 2. So I have negative 1/2 x plus 2 plus 1 times y minus 4 plus 1 times z minus 4. I actually write the 1 in there. I know it's redundant, but it reminds me that I actually put a number there. I might forget to put a number there, so if I don't write anything there, I'm like, wait, did I remember to put the right coefficient there? Now, is there anything wrong with having a fractional coefficient? In theory, is there anything wrong with that? Not at all. Do you like it? No. So I know exactly what Samuel would do. Right? WWSD. Right? Anybody tell me what Samuel would do? Samuel, what would you do?
Multiply by.
Yeah, multiply both sides by 2 or something. Because the right side's a 0. Do you have to? No. But what if that was an odd number? And now you have multiple fractions. Do you like that? No, you like that even less. So probably, let's start with this. Negative 1, negative 4, negative 4. That is a perfectly correct answer. But I think most of us don't like a fractional coefficient if I don't need one. So I would probably multiply it. In fact, if this was a remedial algebra course, do you know what you're actually taught is the rule? Which, by the way, it's kind of a silly rule, but it's actually a really obscure rule. There's something called standard linear form of a line. Not slope-intercept form. That's y equals mx plus b. That's the most useful form. Standard linear form of a line is anything of the form ax plus by equals c, or plus constant equals 0. The funny thing is, the algebra books will say equals c. That's actually incorrect. It actually is always supposed to be 0. But the algebra books, they always put the constant on the other side. It's still the same equation. Standard linear form of a line is anything in this form, and a has to be a positive integer. Period. Doesn't matter what b is. Now, why would you be subject to that as a rule? That's kind of a silly rule, isn't it? Standard linear form of anything. Oh, it doesn't matter how many variables I have. The lead coefficient has to be a positive integer to be called a standard linear form, which, by the way, you're never going to use for anything. So that would mean that I wouldn't multiply both sides by 2. I'd actually have to multiply both sides by -2. I just leave it alone. But that actually is how many have ever heard that before, what I just said? It's very obscure, and you probably haven't done it since you were a little kid. And then you look at it and say, that seems rather arbitrary. And it really is. So I have no use for those kinds of rules because they don't make anything better as a result. So this is an equation of the tangent plane to that hemisphere. And that was a little bit more work because we had to solve. Now, going to Zachary's question, I've kind of looked at it from 2 points of view. I have something that was not a function, so I had to take half of it and make it a function. That required a little bit of algebra and made the calculus a little bit more work. I had something that was a function of 3 variables, so technically it's 4-dimensional, but I gave you an ordered triple, so now you have a level surface. And you could just deal with that, and again, life is very good. What if I had something, let's think 2-dimensional, I have the figure 8. I have my ninja throwing starting, remember that? Count 2. That's not a function, and manipulation is really, really nasty. It's still the same thing. You have to choose a portion of it that is a function. And that can be really difficult. If the equation you were given is really, really nasty, it's difficult. Because that would require you doing some form of implicit differentiation. Now, I want to spend a few minutes today going over that. Now, it's in the video and I explain things, but a lot of people get lost on the implicit stuff because there's a technique involved that's actually quite simple. If you watch the video, you'll see that the technique is actually really, really easy. But if we don't get it right, we'll end up doing way too much work. Now, this is the tangent plane. There's also something called the normal line. Now, I have a normal vector. A normal vector is a direction, but the normal vector, remember, is always oriented at the origin. But I have this point in space. Okay, so I have my surface. Here's the point. You came up with the tangent plane because you came up with the normal vector and the point. Agreed? Now I want that line. I want the line that the normal vector lives on. So therefore, the ABC version isn't going to work. Why? Because that one comes out of the origin. So we've already done the parameterized form of a line before, haven't we? In fact, of all the things in this class, that requires the least amount of work. So on the exam, guess what was the most missed question? Well, it was basically a tie. The equation of the normal line and the cross product. Then followed closely by identifying the cylindrical shapes. In other words, the only problems that didn't require any work whatsoever are always the most missed problems. It's just always that way. The most complicated ones, you know what's really funny? The extra credit problem. More people got the extra credit than got the cross product on page 1.
Thanks.
Significantly more. More than half the people missed the cross product, more than half the people got the extra credit. I throw up my hands and go, well, we concentrate on the big ticket items. So the equation of I don't need this, I need this, and I need this. So let's remind ourselves. How do we do this again? This is a direction. So if I multiply it by t, then I make it infinite in each direction. That's why the parameter goes on this one, not on this one. Sometimes we make the mistake of multiplying a point. A point has no algebraic value. But I can create a vector, and let's call it x minus x naught, y minus y naught, z minus z naught. I'm creating a vector. X, Y, Z is at any point on the line, okay? X, Y, Z is any point on the line, but what am I doing with this guy? I am now saying this vector is going to be a scalar multiple of the direction. And when I do this, what do I get? I get x minus x naught equals t times a1, or simply x equals t times a, well actually let me write it let me write it at. Sorry, it's easier to read. And I'm going to add x naught to the other side. Y equals bt plus y naught, z equals ct plus c naught. I mean, we've done this before, this isn't new. But in case we forgot, oh, I have to create the vector and then I need it to equal to that direction. And that's where the point in space, x naught, y naught, z naught comes in. Now, in this problem here, there's my x naught, y naught, z naught. There's my ABC, if you will. So for this problem here, for that hemisphere, for that point on the hemisphere, so I have a hemisphere, I have a point that's on the other side. I used a negative, so the point's over here. It's right out here, right? A couple units high. I have a tangent plane. I have a normal direction, but now I actually want the line in 3 dimensions. So what would the line be? It would be x equals negative a half t plus negative 2, so minus 2. Y equals 1t plus 4. Z equals 1t plus 4 also. That's it. I'm just using what we already know. Do we use the line very often to answer questions? Not so much. There are questions that will come up in the next 2 days in the application problems of what we're doing the next 2 days. There'll be things like, I have 2 lines in space. How far apart are they? That's a tricky one. Well, if I picked any 2 points, I'd get a different number. So it's really, what's the closest they ever get? Oh, I have a line in space. I have a point in space. How far is that point from the line? Or in other words, what's the closest? So that'd be the orthogonal distance. Does that sound like an interesting question? We're not going to do that one today, but that's an interesting question because that's 3D. Well, why would I care about stuff like finding curves in space and distances from points to curves? I don't know. I do know that Quinn is planning on a solo trip to, was it Mars or Venus? I can't remember.
Mars.
You're going to Mars. So is he just going to get in his rocket ship today and fly? No. He's going to wait till Mars is the closest to Earth. Do you understand? Oh, so there's mathematics to figuring out when and where that closest would be, and that's when you'd want to leave. That's not a joke. That's how we do things in reality. Oh, so being able to calculate distances of things that are not trivial is not just 2 points in space and I'm saying find the distance. I'm motioning it. So think of your line as you're moving on that line, you're moving on another line. What's the closest you ever are? That's an interesting question. Those are lines and that sounds complicated. Can you imagine the orbits, which are 2 elliptical orbits that are not on the same plane? Way more complicated, but there is actually math to do that. It's just geometry. But it's figuring out, the when and the where, the closest, so that I could do the calculation. I find that to be really interesting. Cool at the least. So, equations of tangent planes, fairly simple. So now I'm going to show you something where we can use this to answer a question that you just answered today on the quiz. All right, so I'm going to do this. On your quiz, f of 0.98, 2.03, 3.01. Okay? So if you watch the video, the most important thing is identifying what point? The happy point. I said in all seriousness, the happy point. I don't want to work with that. That's icky. So what's the happy point?
1, 2, 3, 2.
Yeah. So this is x naught, y naught, z naught. What's this? This is x naught plus change in x, y naught plus change in y, z naught plus change in z. And the estimation using this value is only good if the delta x, the delta y, and the delta z are relatively small. So in other words, I chose values that were very close to the integers. The process does not change if I drift further away. The accuracy of my answer is compromised. So if I was using like 3.5 rather than 3.01, I'm much further away, right? I've escaped. It'll still work, it just won't be as close. That's why we like problems of this nature. What if I had used 4 instead of 3? I could, but I'm really far away now because 0.99 is really big compared to 3, but 0.01 is really small. So we did this problem using the exact same way of doing it like we did in Calc 1, okay? I want to do this using what we did today. In other words, I want to use the tangent plane. Ooh. So I want to use the tangent plane. Everything on the quiz was correct, but you didn't know this. I'm going to give you literally an alternate way of looking at the same problem. And obviously, we're going to use the same information, the same sorts of derivatives. So here's the question. What is the equation of the tangent plane that goes through happy point? Okay, well, let's see. I need to take the gradient of f. Walk me through this, because you actually did this on the quiz already, you just didn't call it a gradient, you did individual partial derivatives. So the gradient would be what? 2y squared minus 12x squared z. Now with respect to y, it would be 4xy, and with respect to z, it would be negative 4x cubed. Is that correct? Oh, yeah. Does that look right? Is that what you did on the quiz? I think that's what you, yeah, that looks like what you did on the quiz. Now, what is the gradient evaluated at 1, 2, 3? Go slow. So evaluated here would be 8 minus 36, I think that'd be negative 28. In fact, you did this already, and you got 8, and I believe negative 4. Okay? These numbers should feel familiar because you did these, but you did them from a different point of view with a different goal in mind. I want the equation of the tangent plane. So now I want to take negative 28, 8, 4, and I want to dot it with x minus 1, y minus 2, z minus 3. And I want to get 0. So now I have negative 28x.
Your 4 should be negative in the first fraction.
Oh, thank you. Thank you. So negative 28x plus 28 plus 8y minus 16 minus 4z plus 12. I think this looks right. 28 minus 16 is 40 minus 16 minus 24 equals 0. Now, I think I did everything right. Is there a way to check? Let's assume that this is right here. Could I have distributed badly? There's a simple check that we sometimes forget. I just used 1, 2, 3. Plug in 1, 2, 3. Now, I'll know if I just, is it possible we made a sign error because we distributed badly? Well, you wouldn't, but you know somebody who does that all the time. That's just their thing. So negative 28 plus 16 minus 12 minus 24, does that equal 0? Real quick check. Negative 28 plus 16, hold on, did I write that correctly?
It should be a plus 24.
Hold on. I got a boo-boo somewhere, don't I? And this is how we're going to find it. 8 minus 16 plus 20. All right, okay, good. So negative 28 plus 16 plus 12 plus 24. No, something's still not right. This is why we check. Okay. Does that work? Does that equal 0? Good. Okay. It's correct. But you can always check it. So this is the equation of the plane passing through that point. So how am I supposed to use this to help me with that? Well, what is f of 1, 2, 3?
-4.
What is it?
-4.
It's -4. What I want to do is I want to actually take these values right here and put them in there. Okay? Let's take those values right there and put them in there. And here's what I'm going to tell you. F of 0.98 comma 2.03 comma 3.01 is going to be estimated by -4 plus whatever I get when I put those in here. Remember, the tangent plane at 1, 2, 3 is going to give me 0. But what are we doing? We're drifting on the surface just a tiny bit, so we're leaving the tangent plane just a little bit. So when I use those numbers and put them in here, I'm not going to get 0, I'm going to get something else. Agreed? I'm going to put them in here. So forget the equal 0 for a moment. I'm just going to put the numbers into here. It equaled 0 at the place that we at 1, 2, 3. It's not going to equal 0 anywhere else. So with your calculator, let's do this. So in other words, I'll write it like this. Plus -28 times 0.98 plus 8 times 2.03 minus 4 times 3.01. Hopefully I wrote it down correctly. I don't have a calculator.
So we're plugging in the actual points.
The equation of the tangent plane we just came up with.
But instead of the dx and the dy and the
Yeah,
dz, it's like
this is, I'm actually using the tangent plane this time.
Okay.
What we did before was, everything was valid. We did something else. Now I said, let's use the tangent plane. The tangent plane to happy point leaves the surface. Okay? The tangent plane evaluated at 1, 2, 3 will be 0. So what I want to do is, right, I'm moving down the surface a little tiny bit, but I want to use those values on the tangent plane. And that difference, I'm going to get something slightly different. This should not be 0. But if I add this to the functional value at happy point, by the way, what do you get? Make a number?
-3.24.
-3.24. Is that the answer you got on the quiz? So is that a good thing? Yeah. I'm using all the same numbers. So let's go backwards a little bit. What if you had done it this way instead? -28x minus 1 plus 8 times y minus 2 minus 4 times z minus 3. Let's say you didn't distribute. Now when I replace x with 0.98, isn't that value going to be my dx?
oh, okay.
Do you see it now? You're like, if I replace the y with 2.03, then this is going to be the dy, and it's going to be the dz, and I've got, you actually did -28 dx plus 8 dy plus -4 dz, and then you added that to the, so in other words, are you doing the exact same mathematics in general? Yes, but you did it by specifically using the tangent plane. So now I'm showing you that the equation of the tangent plane to this surface could also be used to do the estimation. And because every step you did, you had done a version of it. That's kind of interesting. You might find it cool, you might not, but I did this by finding the equation of the tangent plane and then using that to do my estimation. You can always do that. What you did was absolutely correct and valid. So is this, because you're using all the same information, the same partial derivatives. You just decide to come up with a plane first. I don't know, I think it's kind of cool. It's kind of a cool application. Now, I want to go backwards a little bit because some of the stuff that you're responsible for, I need to make sure that you understand it thoroughly. So what I prove, I'm not going to go through the entire derivations again because they're kind of long-winded, but what I wanted to show you was implicit differentiation in general is actually very simple if I look at things as a three-dimensional problem. Okay? Calc 1. You've got x squared y plus, I don't know, let's keep it ugly here. Tangent xy equals e to the x. All right, that's pretty nasty. And you want to find dy dx. Now, the Calc 1 approach, there's no way you could isolate the y. Agreed? It's not possible. So what we do is we say, I cannot solve explicitly for y. I cannot write y equals a function of x. That's not mathematically possible. It'd be like a circle. You can't write y equals a function of x. You need plus or minuses. That's not a function. But I can say I'm going to assume that y is a function of x, so y is implicitly defined as a function of x. That's why it's called implicit differentiation. And what we did in Calc 1 was we simply differentiated both sides with respect to x. We could have done it with respect to y, except that I want this. And that says that y is a function of x. So, what do I got? Now, y is a function of x. Y is not a variable. If y is a variable, then every time I take a derivative with respect to x, I'd have to get 0, wouldn't I? This isn't Calc 3 yet. Oh, I'm assuming y is a function of x. So when you see y, think f of x. Don't see variable, see function. So first times derivative of second plus second times derivative of first. Tangent of thing, the derivative is secant squared of thing times derivative of thing. xy. So first times derivative of second plus second times derivative of first. And on the right-hand side, I just get the e to the x. Now, I'm done with the calculus. Now it's just algebra. I have to isolate the dy dx term, which is absolutely always possible at this point. So, probably need to distribute right here. So let me clean this up a little bit. So that's x squared dy dx plus how about 2xy? So how about I write this one as x secant squared xy times dy dx plus y times the secant squared of xy, and that's all equal to e to the x. Now what I need to do is get the dy dx terms on one side and everything else on the other, and then I can easily solve. Okay? So I've already got these guys here, so I'm going to send this guy and this guy. That's my formal mathematics there. I'm going to send those guys packing. Okay? Send those to the other side. So on the left side, I now have x squared plus x secant squared xy all times dy dx. And on the right side, I now have e to the x minus 2xy minus y times the secant squared of xy. Okay, so far so good? If I make a mistake, please point it out, because I don't like boo-boos here. So finally, dy dx equals all of that over all of that. Now, if it were possible to factor and cancel or simplify, you would always want to do that. But we all agree this was long-winded. Agreed? This was not a trivial process. Now, I'm not going to go through the entire derivations. That's on the videos. But I showed you that if I look at this as being a level curve of a three-dimensional function, then this process becomes much simpler. Well, I need to create a three-dimensional function. So how about if we do the following? Let's let g of x comma y, doesn't matter what letter you use. throw that over. X squared y plus tan xy minus e to the x. Therefore, when this equals 0, my original problem is that particular level curve. Agreed? Now, the first and foremost is you have to get everything to the same side. A common error is that people will say, let me call the left side g of xy, and then that equals e to the x. No, that would be incorrect. Any conclusion you get would be completely different. I need everything on the same side, and now I define a new function. And then what we showed, again on the video, I showed you that dy dx is equal to the negative of the partial of g with respect to x. It's fairly easy to remember. There's a negative sign and you flip these over because of how you have to solve. How many have actually watched that so far? It's actually really simple algebra, isn't it? It's not complicated. But what I did was I started by creating a three-dimensional, took the derivatives and then solved for dy dx, and then that's what you end up getting. So, okay, what's the partial of this with respect to x? Well, that would be what? 2xy plus secant squared xy. With respect to x, y is my derivative, correct? You all agree? I'll put the y in front. And with respect to x, that would be then minus e to the x. Now, what's the derivative of this with respect to y? The x squared plus secant squared xy. Now, the derivative with respect to y, I'd have x as my chain rule factor, and then there'd be nothing there. And you do a quick check, these answers are exactly the same. Except that was easy. I actually can't make a problem that's difficult for implicit differentiation. It's actually easy 100% of the time. Why? We changed our point of view. We said, let's not look at this horrific thing in the xy plane that's not even a function. I mean, this could be my figure 8, you know, with donuts in the middle and all sorts of weird stuff. But if I said, let's step back and think of this as a slice of a three-dimensional function, we know that's absolutely correct for anything that exists in 2 dimensions. If you have an equation in 2 dimensions, throw them on the same side and call that g of xy or f of xy. You can always do that. But now taking the partial derivatives was rather trivial, wasn't it? You all agree that that was really, really simple. It just wasn't that bad. Wow. Now, the second question is, does this still work if I go to more variables? And the answer is actually yes. And I'll do a slightly simpler problem here. This one was kind of gnarly and long and everything. So let's suppose that z is a function of x and y. But I have something of the form, I have something evil like this. I've got a sine of, how about, of x, z, minus z squared equals, I'll just do one more, e to the yz. Okay, how's that? Oh, by the way, I want to find the partial of z with respect to x. You thought the first one was awful, you know. So if you look up evil in the dictionary, this won't be the first definition, it's probably like the 5th. But it's in there, you know. Doing an implicit differentiation problem with multiple independent variables. That's what I'm asking you to do. And we'll go really slow. I want the partial of z with respect to x. That means I have to do this to both sides. Okay? Now I'm going to walk you through it, and then I'm going to show you the shortcut, just to verify that, yes, it is the same. I can tell you the result, I'd rather show you, because you're more likely to believe it. So the derivative of the sine function is the cosine function. But since z is a function of x and y, I have a product rule I have to perform here. Yikes. So first times derivative of second, which would be partial of z with respect to x, plus the second times the derivative of the first, which would just be 1, because I'm differentiating with respect to x. So I think of this as function squared. So minus 2z to the first power times the partial of z with respect to x. I'm not differentiating with respect to y. Y is an independent variable, but z is not. So what is the derivative of e to the thing? It's e to the thing times derivative of thing. And when I'm differentiating with respect to x, y is a constant, but z is not. So it would be y partial of z with respect to x. Everybody follow that? I'm still differentiating with respect to x, and z is a function of x and y. Now, this maybe wasn't as bad as the previous, or maybe it was worse, I don't know. So let's do what we did before. Let's gather terms. I have to distribute first, though. So this is x. Okay, I'm not that good. Blue cap. Okay, and then minus 2z partial of z with respect to x equals, how about y e to the yz partial of z with respect to x. There we go. All right. I need all of the partial on the same side. So it looks like I'm going to send that guy, and I'm going to send that guy. Does everybody agree? I think that's correct. I don't know. I could be wrong. Like I said, I could be wrong. I usually am, but maybe not this time. So I'm going to have an x cosine of xy minus 2z minus y e to the yz all times the partial of z with respect to x. And that's going to equal the negative of z cosine xy. Or xz. No. Hold on. Did I write that incorrectly? That should be, sorry, that should be a z, not a y. Where's that pen? Lost that pen. Does that look right?
And the other one too?
Oh, yeah, the first. No, that's a yz, that's an xz. So I had dropped, oh, yeah, that's a, thank you. Z. Well, I'm standing that close and I still miscopied it, didn't I? So let me quick check. So, first. Okay. Some of you might be asking, why didn't we do a product rule on this one? I'm differentiating with respect to x, so the derivative of the y term would be 0. So you treat y as a coefficient in that case. That's why there wasn't a product rule. So this is xz. 2 minus equals x. Oh, okay, there we go. Ugh. So my answer is that over all of this. All right. That it is what it is. I don't know if it was better, I don't know if it was worse. Now the question is, can we do the same thing we just did when there was only 2 variables? Well, let's make this problem a level surface of something 4-dimensional by throwing everything on the same side, and let's call it, I see, since I've already used little f, I can't call it f of x, y, z. Everybody understand? I've already used little f, so give it a different name. Call it g. So I'm going to say let g of x, y, z equal, get everything on the same side, so I'm just going to move the one on the right over, minus z squared minus e to the yz. I think I wrote that correctly. Yep. So here's what I want to do. I want to find, I'm going to do them slowly. I want to find these 2 partial derivatives. I am not interested in the y at all because this instruction only had to do with x and z. So what is the partial with respect to x? It'd be cosine xz times the derivative of xz with respect to x. So it would just be z, wouldn't it? Okay? Now, What is the, right now, remember, we're treating x, y, and z now as independent variables. So what's the partial with respect to z? So you now say cosine of xz times x. With respect to z, it'd be minus 2z. With respect to z, you'd say minus e to the yz times y. So, I would like you to find negative what? Gx over gz. Using the exact same rule we did before. Flip those, put a negative sign. So what's the negative of gx over gz? Well, let's see, it's going to be negative z cosine xz over x cosine xz. Hopefully I can get this in here. Minus 2z minus y e to the yz. A little bit tight. Same answer? Crowd goes wild, confetti everywhere. I don't need to ask you which one you like better. One of them was gnarly, one of them was actually quite simple. As long as you're taking your partial derivatives correctly, which most of you are going to do almost 100% of the time, because the partials are just so much easier. They're just like regular derivatives. This is beautiful. This works no matter how many variables. So implicit differentiation, which everybody fears, and you rightly should fear. Implicit differentiation in Calc 1 is gnarly because of the way you have to differentiate. And then after you're done differentiating, the algebra might be actually more work, all the gathering of terms. Now that we know this, I always laugh because I get asked this almost every semester. You know, someone will say, why didn't they just show us this in Calc 1? You're doing implicit differentiation on like your 5th lecture of Calc 1. Don't really think I could show you partials and all their manipulation on your 5th lecture of Calc 1. Remember, you learned implicit differentiation probably the day after you learned the trig derivatives, but way before you learned exponentials and logs and inverse. You learned implicit really early on. It's actually at the beginning of the course. So yeah, you couldn't have learned this back then. There's too much in between. But now that you know this, you don't fear implicit anymore, because you're looking at everything as a cross-section of something bigger. And when you do that, you're taking something that's not a function in the xy plane, but it is a function in 3-space. And once you do that slice, our circular paraboloid is a simple, friendly function in 3D, but all the slices are circles, which are not functions in 2D. That's why looking at it as a 3-dimensional problem is just so much easier. Okay? Everybody cool with that? So this is not a major application, it's just a really cool application of chain rule, because that's all we're applying. So now I want to go back one more thing, because I like tying everything together. Many of you were in Calc 1 with me. I don't expect you to remember details, but in Calc 1, we start the problem. I don't think we've done this problem in this class, but A is the radius, okay? X squared plus y squared equals a squared. And I would like to find the derivative of y with respect to x. So in Calc 1, this is early in Calc 1. This is quite literally maybe the second day you've done derivatives. So there's no, I'm introducing implicit. So I said, well, can I consider the top half as y equals the square root of x squared minus y squared, and the bottom half as y equals negative? Is this legal? Yeah, it's correct. And so what I want to do is independently find each of these derivatives, because we can. We know how to find these. We don't have to be clever. So first thing I'm going to do is think of this as a squared minus x squared to the 1/2. And this one as the negative of a squared minus x squared to the 1/2. Now, I'm going to walk you all the way through, and I'm going to show you there are many, many, many ways. I've actually now got 4 ways to find the slope of the tangent line. 4. And the beautiful thing is I'm going to find all of them completely different, and they're all going to agree, which confirms certain things too, but also shows you have routes. You often have choices with how to do a problem. So when I do the top half, my dy dx, 1/2 a squared minus x squared to the negative 1/2 times what? What's my chain rule factor? Negative 2x. A is a constant. Okay? If I put this back, I'm going to write it like this. Negative x over the square root. It reads easier. Okay, everybody agree with that? Now this guy. Negative 1/2 a squared minus x squared to the negative 1/2, and again times negative x squared, or excuse me, negative 2x. What am I thinking here? All right, so I'm going to write that as, weirdly, I'm going to write it like this. Cancel the 2's. Negative x over negative square root. Mr. Brown, shouldn't you just cancel those negatives? Yeah, usually, but I'm not gonna. True or false? Look at your denominator. It's the square root of a squared minus. It's exactly what y is. What's my denominator? Now, usually when you take a derivative, right, y is a function of x, you think of your derivative as being nothing but x's. I just took the derivative of the top and bottom, and we got these two independent answers, which were not the same. But both of them ended up being exactly negative x over y, didn't they? That's a good thing. Think of this. But you'd say, normally I wouldn't represent a derivative that way, but actually you might find this to be more useful. Okay, now let's look at it implicitly. If I had done this implicitly, and this is part of the reason you should like implicit, well, okay, better than this. Okay, I have 2x plus 2y, but y is a function of x, so times dy dx equals the derivative of the square of my radius, and that would be 0 because that's a constant. Oh, okay, so 2y dy dx equals negative 2x. So dy dx equals negative x over y. Good thing? Yeah, more of a, okay. That's implicit differentiation. Let's use what we just learned today. Let's look at this as a slice of a three-dimensional thing. So I'm going to let, I haven't used f yet, so I'll call it f of x, y. Let f of x, y equal x squared plus y squared minus a squared. You all agree with that? I'll write them out this time. What is fx? What is fy? Again, there's no dy dx terms because I just made x and y independent variables. Lest we forget, I've made this a three-dimensional problem now. Okay? What I did, essentially, if you're wondering what three-dimensional problem did I just make it, here's what I just did. This is below the xy plane. When it reaches the xy plane, that means that z equals 0. And when z equals 0, what do I have? X squared plus y squared minus a squared is 0, or x squared plus y squared equals a squared. My cross section in the xy plane is exactly that circle over there. Does everybody see that? That's important. I just made it so that circle there is exactly this cross section in the xy plane. But it doesn't matter. It doesn't matter which one I use, because what are we now saying? dy dx is the negative of this guy over this guy. Again, same thing, but you might argue that this was the easiest of the bunch. Right? Do you see the consistency? Like, it still works. Now, I said there's one more way. A non-calculaic way. I was asking you to find the slope of that tangent line. What do we know from geometry about a radial segment and its tangent line at the point of tangency. We know they have to be orthogonal. Another way of saying it is the closest point on the tangent line to the center is the point on the circle. And the closest point is always the perpendicular distance. Do we know that from baby algebra? That the perpendicular, I flip it over and change the sign? I think that's the coolest one of all. You mean, I learned that in 9th grade? Yeah, well, in a sense. You already knew the slope of the tangent line by just simply using the slope of the radial segment here. You know this slope is y over x, right? Change in y and change in x. So this one has to be the, sometimes we refer to as the negative reciprocal. We just came up with the same answer 4 ways. That's actually very comforting that it didn't matter how I look at the problem, I got the same answer. If the question is asked, and I don't mean in this class, I mean in a different class. You're in physics, you're in somewhere else. If you're going to get the right answer, does it truly matter how you get it? As long as your method is sound and you understand it, and you can actually convey that idea to someone else. I had a situation a couple of years ago, it was very interesting. I had a student, he was just killing it, he had killed it in Calc 3, he was killing it in linear algebra, and he was taking a physics class, and they had to solve a problem. And it was a several variable problem, and so he used matrix. He used what he knew from linear algebra, and it was a trivial solution. And I won't tell you which campus or which instructor, but the instructor marked him wrong, said, no, you can't do that. And the student said, but I represented everything perfectly, and this was the easiest way. And they even asked me, I said, yeah, the easiest way. The instructor said, no, you have to do it the complicated way. And the student said, why? The instructor says, because I don't know linear algebra. And I thought to myself, first of all, that sounded extremely unprofessional. And first of all, I don't think I would ever admit that. But secondly, that is exactly how the problem should have been solved, because the way the instructor did it took like 2 pages, and the way the student did it took, a block, and it was really easy to understand. And the instructor used, I must solve systems of equations from baby algebra, or substitution and addition and doing all this stuff. And I thought, no, the class wasn't linear algebra, but he used something he learned to solve an algebraic problem in a physics class. That'd be like saying you're in physics and you used calculus to solve a calculus problem, but they say you can't use that calculus. But it's a calculus problem. There are really no limits. Now, in our class, I want you to know all of these, but today I want you to do this. Why do I want you to do this? Because it's the newest thing? No, it's the easiest thing. it's the one you're least likely to mess up. And so it's the path of least resistance. I use the circle. But the previous examples were far more complicated, weren't they? Okay? Go ahead and turn that off. All right.